Hey everyone! Have you ever wondered why water molecules are bent? Or why methane molecules form a perfect tetrahedron? Well, that's where VSEPR theory comes in. The valence shell electron pair repulsion theory helps us predict the shapes of molecules by focusing on how the electron pairs around an atom arrange themselves in space. Imagine you're trying to pack a suitcase. You'll put things in such a way that they take up as little space as possible, right? Well, electron pairs do the same thing. They repel each other, pushing away to maximize the distance between them, and that's what gives a molecule its shape. Today, let's explore how VSEPR helps us understand these molecular geometries. Now, let's dive into the core ideas of VSEPR theory. The first postulate is that the shape of a molecule depends on the number of valence electron pairs, both bonding and non-bonding, around the central atom. These electron pairs are like magnets that repel each other, so they arrange themselves as far apart as possible. That brings us to the second postulate. Electron pairs push each other away because they all carry a negative charge. To minimize this repulsion, they take up specific geometric positions. This leads us to some familiar shapes like linear, trigonal planar, and tetrahedral. It's fascinating to see how this theory explains the structure of molecules from simple water to complex compounds. And remember, multiple bonds, like double or triple bonds, act like single bonds in the VSEPR model, meaning they only count as one electron pair when determining the molecule's shape. Let's take a closer look at how these electron pairs shape molecules. For example, when we look at methane, spelled CH4, the carbon atom has 4 bonding pairs of electrons. These electron pairs push each other as far apart as possible, forming a tetrahedral geometry. In contrast, in molecules like carbon dioxide, spelled CO2, there are 2 bonding pairs, so the molecule adopts a linear shape. Similarly, water, spelled H2O, has 2 bonding pairs and 2 lone pairs, causing the molecule to take a bent shape instead of a linear one. Each of these shapes minimizes electron repulsion and helps explain the physical and chemical properties of the molecules. These shapes aren't just theoretical, they affect how molecules interact with each other in real life. Now, let's talk about lone pairs. These are the electron pairs that aren't involved in bonding, but they still influence the shape of a molecule. Lone pairs occupy more space than bonding pairs, so they cause greater repulsion. For example, in ammonia, spelled NH3, the nitrogen atom has 1 lone pair and 3 bonding pairs. This causes the molecule to have a trigonal pyramidal shape with bond angles less than 109.5 degrees. In water, spelled H2O, the 2 lone pairs on oxygen push the hydrogen atoms even closer, leading to a bent shape. The presence of lone pairs distorts the geometry and reduces bond angles, and this is crucial when predicting the structure of molecules. Alright, now that we understand the basics of electron pair repulsion and lone pair effects, let's learn how to predict molecular shapes using VSEPR. Here's the process. First, identify the central atom and count its bonding and lone pairs. Then, determine the total number of electron pairs around the central atom. This will tell you the geometry. For example, if there are 4 bonding pairs around the central atom, you know it's a tetrahedral shape like in methane, CH4. If there are 2 bonding pairs and 2 lone pairs, like in water, H2O, the shape will be bent. This method works wonders for small molecules and helps us understand molecular behavior, from how they react to how they interact with light, heat, and other molecules. While VSEPR theory is fantastic for predicting shapes, it's not perfect. It doesn't account for the exact nature of chemical bonds or electron distribution in detail. For example, it can't explain why molecules like don't follow typical VSEPR predictions. That's because larger molecules or those with transition metals might require a more complex approach, like molecular orbital theory. But even with these limitations, VSEPR gives us a simple yet powerful tool to understand the geometry of many molecules, especially those involving p-block elements. To sum up, VSEPR theory helps us predict the shapes of molecules by considering how electron pairs in the valence shell repel each other and arrange themselves to minimize that repulsion. We learned how this theory explains everything from the linear shape of CO2 to the bent shape of H2O. While it has some limitations, especially for complex molecules, VSEPR is an essential part of understanding molecular behavior. So, the next time you look at a molecule, think about its shape. It's not just a random arrangement but the result of electron pairs trying to avoid each other. Thanks for joining me in this exploration of molecular geometry. See you in the next lesson, where we'll dive into another exciting topic in chemistry.